Unit 1A, Lesson 4. This lesson will align with 6.7 in your textbooks. The one standard we are going to cover in this lesson: know the fundamental theorem of algebra, show that it is true for quadratic polynomials. For you history buffs out there, this gentleman is Carl Gauss. He first proved the fundamental theorem of algebra in 1799. We'll talk about Carl Gauss more in pre-calculus when dealing with Gaussian elimination, referring to matrices. The fundamental theorem of algebra, there's two different parts to this. Essentially, they're saying the same thing depending on the textbook or the level of mathematics. How they word this theorem is different, okay? What you're going to see in your textbooks is the yellow portion. What we're really taking from it, or what you may see later on, is in the green portion. Yes, I used yellow and green because I'm a Packers fan, so you just have to deal with it if you don't like that. So the yellow portion, the fundamental theorem, well, I should say theorem, the fundamental theorem of algebra states that every polynomial with degree n greater than 0 and complex coefficients has at least one complex root. Alright, like I said before, that's what you're going to see in your book. If you have a polynomial, complex coefficients, there's going to be at least one complex root, whether it's real or imaginary. The green portion, what we're really taking from this, the corollary of the fundamental theorem of algebra states that every polynomial function with degree n has exactly n solutions, with repeated solutions being counted for the number of times that they are solutions. For example, if we have x minus 2 quantity squared, that makes 2 a solution twice. Alright, we'll talk more about this later. What this theorem basically says, if we have a cubic polynomial, for instance, x cubed plus 2x minus 1. According to the fundamental theorem of algebra, there's going to be at least one complex root. More specifically, there's actually going to be 3 complex roots. In the first example, we want to identify the number of complex zeros for each polynomial. First, we have f of x equals 7x to the 4th minus 21x plus 3. So we're looking for the n value, which refers to the highest degree, or the degree of the polynomial. So if we look at all these terms, we have 3 terms. The highest degree is 4. So there will be 4 complex zeros. They may be a combination of real or imaginary. There may be some repeated, but there's going to be 4 total. Next function, g of x equals radical 3x squared minus 4x cubed. Again, we're looking for the highest degree, which is in the second term, it's 3. So there's going to be 3 complex zeros. And the last one, h of x equals 17x plus 2x squared minus 31x to the 6th. The highest degree is 6, so there is going to be a total of 6 complex zeros using the fundamental theorem of algebra. Now we're going to grasp the true meaning of the fundamental theorem of algebra and apply it to answer this question. Can a quadratic polynomial have exactly one real root? So what I want you to do, pause the video now, think about this, and try to come up with an answer. Can a quadratic polynomial have exactly one real root? First of all, what is a quadratic polynomial? Well, it's x to the 2nd power. If our polynomial has a degree of 2, that means there must be 2 complex roots, whether they're real or imaginary. So if we have 2 total complex roots, and one of them is real, okay, let's just suppose one of them is real, that implies there must be one imaginary solution. But if you think back to the beginning of this unit, we had a theorem, the complex conjugate theorem, that says if you have a complex root or an imaginary root, they occur in pairs. So if we have one imaginary, that means there must be one that is a pair to it, the conjugate. Well, 1, 2, 3, that would imply we would have 3 total roots. This would no longer be a quadratic. So the answer to this question is no. You cannot have a quadratic polynomial with exactly one real root. For your 2 roots, they're either both going to be real or they're both going to be imaginary, because we know the imaginary roots occur in conjugate pairs. In this last example, we want to determine if each polynomial could have the number of given real roots. So first we have f of x equals radical 7 x to the 5th plus 3x minus 8. We know there's going to be 5 total roots. So what you need to determine, is it possible for there to be 2 real roots? Exactly 2. Okay. Well, if you had exactly 2 real roots, that would mean you have 3 imaginary, and you can't have an odd number of imaginary roots because they occur in conjugate pairs. So the answer to this question would be no. It is not possible to have an odd number of imaginary roots. Next, we have g of x equals 14x squared plus 11x cubed. Highest degree is 3, which means there's going to be 3 total roots. You need to determine, is it possible to have 1 real root? Exactly 1 real root. Well, if you have exactly 1 real root, that means there's 2 left. So you have 2 imaginary roots. Those could be a conjugate pair. So yes, this would be possible. It's possible to have a degree 3 polynomial with exactly 1 real root. And the last one, h of x, which is equal to 3x to the 4th plus 7x minus 34x squared. Highest degree is 4, so there's 4 total roots. Is it possible to have exactly 2 real roots? Well, if you have 4 total and 2 real, that implies there's 2 imaginary, so those could be a conjugate pair. So this would be yes as well. It's possible to have a degree 4 polynomial with exactly 2 real roots. The main focus of this lesson was the fundamental theorem of algebra. You need to make sure you understand both wordings or phrases for this theorem. The first one, where it says if you have a polynomial with complex coefficients, there's going to be at least one complex root, or the corollary to it, which says if you have a polynomial with degree n, then there's going to be exactly n roots, whether they are real, imaginary, a combination, whether they're repeated. Just make sure you understand both wordings for that theorem. Okay? And also be able to complete the examples where if I give you a polynomial, be able to identify how many complex roots there could be.